Welcome back to day 36, our introduction to Taylor Polynomials through e to the x. This is part of our power series topic, my favorite topic in AP Calculus BC. Last class we learned how to build a better tangent line, and in fact we stopped calling it a tangent line and we called it a tangent function. So if you want to look back at what you did before, it's maybe not a bad idea, because what we're going to do is build off of that. In particular, last class we compared two equations near the end. We said, okay, we have the equation f of x equals e to the x, but I can actually create the graph of e to the x, kind of. And we started by building a tangent line, and we said, okay, our tangent function, well, normally a tangent line, right, would be, and I'll try to remind you very quickly, we're doing this at 0, by the way, f prime of 0 times x minus 0, technically to the first, plus f of 0. But we said, hey, why don't we rewrite this slightly differently? Let's do f of 0, I'll leave a gap, and then plus f prime of 0 times x minus 0 to the first. Right, that should be a 1 over here. Okay, and then I said, well, in order to visualize a pattern, we could also say that this is x minus 0 to the 0th. And from there, we took it and ran, and we said, okay, well, let's go ahead and go out to 5 terms. 5 terms, let's say this is one term, a second term. I think 5 terms is going to go out to the 4th power. So really what we're doing then is we're saying, okay, so t of x is going to be, and I'll write out the whole thing just so we can get used to it. The more you write this pattern, the better you're going to be, I promise. So f prime of 0 times x minus 0 to the first plus f second derivatives, double prime of 0, x minus 0 to the second, third derivative, and the 4th derivative, right? Something like this. Okay, now evaluating all of these, technically each of these needs to be plugged in to the original function. Oops, let's just say of 0. To the original function or its derivatives, whatever it says. However, as we discussed last class, the derivative of e to the x is just e to the x, and every time we evaluate this at 0, the answer is 1. So simplifying this just a little bit, and I'll simplify once more after, each of these is going to be 1. And actually x minus 0 is just x, isn't it? So we get 1 times x to the first, 1 times x to the second, and you get the idea. And then, of course, finishing our simplification, this whole thing is just 1. Anything to the 0th is 1, 1 times 1 is 1, and this is x, x squared, x cubed, and x to the 4th. And my hypothesis then, or something we'll check shortly, is that this equation is e to the x. Well, one of the easiest ways to check if this is actually e to the x is, of course, to graph e to the x and then graph my tangent function or my polynomial approximation. So I'm going to go ahead and pull this up really quickly. Looks like this over here. I already have e to the x graphed, nothing too bad. Let's go ahead and graph 1 plus x squared plus x cubed plus x to the 4th. Boop. Is that the same as e to the x? Well, no. Now remember, the reason that we built all of this out is because we're trying to make the point at 0 on the purple graph have all the same properties as the point at 0 on e to the x. Currently, they will be equal to each other. They will have all the same derivative properties, I think, all the way down to the 4th derivative, right? That 4th power lets us take the derivative 4 times before things turn to 0. But the issue is e to the x has an infinite number of derivatives. So to really make the point at 0 match, we need to continue going out. But I think the pattern here is very easy to see, isn't it? Couldn't I start adding a couple more terms, plus x to the 5th, plus x to the 6th, plus x to the 7th, and as I add more terms, it does look like it's a little bit better in this small interval, kind of between -1 and almost 1 over here. But it's not really mimicking the rest of the graph of e to the x. And in fact, if we did a perfect job, this purple graph should really be perfectly matching up to e to the x. And it's not. It's kind of just stuck right here, which means I think that we're missing something else. Well, what are we missing? Well, the easiest way to figure out what we're missing to make this an even better tangent polynomial is to just start comparing our derivatives, because I made the supposition, the hypothesis, that this tangent had the same derivatives of e to the x, at least at an x value of 0. So was I right? Well, let's double check all of this. So I'll start with just the original function f of x, and I'll do that one in blue. And of course, the derivative is just e to the x every time. And then we'll start evaluating each of these at 0, just seeing all the properties that the x value of 0 has. The first property is that it has a y value of 1. The second is that 0 has a slope of 1, a concavity of 1. The concavity is changing by 1, and the change of the concavity is also changing by 1. Cool. Well, what about my tangents here? Well, I'm going to have to go through and take a bunch of derivatives up here, but I'm going to start with the original equation, this guy right here. Okay, and then, of course, when I evaluate this at 0, all of these become 0 and just leaves us with 1. All right, let's take the derivative. Derivative of my tangent, well, this becomes 0. I'm not even going to write that. I think we get 1 plus 2x plus 3x squared plus 4x cubed. And then we evaluate at 0. Again, all of these become 0 and leaves us with 1. Cool. These two match perfectly. It shows us at an x of 0, the tangent function and the original function have the same properties so far. All right, second derivative. 2 plus 6x plus 12x squared. Evaluating at 0, this becomes 0. Uh-oh. Now we got 2. It's supposed to be 1. What this is telling us is at 0, my tangent function actually has double the concavity as it should have. All right, let's continue on down. 6 plus 24x. This becomes 6. Uh-oh, 6 times the rate of change of the concavity. And the last but not least, 24. Oh my gosh, it's getting worse. And in fact, if I had had an x to the 5th term here, by the time I got to the 5th derivative down here, then it would have been really, really off, because e to the x is 1s all the way down. And these are getting worse and worse. They're veering away after this first derivative, because there's one thing we haven't taken into account. And what we haven't taken into an account is the power rule of polynomials. And what the power rule tells us is that each derivative actually gets multiplied by this power up here. So originally, all of these have 1s, and that's great. We like there to be a 1 here. It matches the ones over here. But as we go through, let's look what happens to this one. It first gets multiplied by 4, then gets multiplied by 3, then by 2, and then by 1, which doesn't really change. So we might want to think of how we'd have to go backwards. Right? These two already match, so let's maybe think about what I'd have to do to the second derivative to make it match this guy over here. Right? And there's a little bit of space here. You might have to write small, but I think you'll be okay. T double prime of 0 currently equals 2. But I want the second derivative to equal 1. What do we have to do? Well, of course, we have to divide by 2. And keeping everything equal, that would mean we have to divide the second derivative by 2, and that would give us our correct answer of 1. Same thing, the third derivative at 0 is currently 6. I would need to divide that by 6 to bring it back to the wanted 1. And of course, the fourth derivative is equal to 24. So I'd have to, of course, divide by 24 to get to 1. But it's kind of weird because we're having to divide by different numbers here. It doesn't look like there's too much of a pattern. Oh, but wait, I think we actually do know a pattern here. Haven't we seen the numbers 2, 6, 24? In fact, the next one is 120 before. Well, I think we have, and it might help if we rewrote them like so. 2, isn't that 1 times 2? And 6, isn't that 1 times 2 times 3? 1 times 2 times 3 times 4, and the next one 1 times 2 times 3 times 4 times 5. Aren't those factorials? Oh. So maybe instead of writing divided by 2, we could do 2 factorial, 3 factorial, and 4 factorial. Now, why are there factorials? Well, I actually already showed you, right? If you look at that power rule, first we multiply by 4, then by 3, then by 2, then by 1. 3, then 2, then 1, and so on and so forth. So we're off by a factor of a factorial every single time. So how could we make our tangent function better? Well, let's introduce some factorials. So you're going to have to write again a little bit small here. I wanted all this to fit on the first page. And my tangent function originally was 1 plus x squared plus x cubed plus x to the fourth. And now we're dividing by factorials. So let's work backwards from x to the fourth, because we said to make that correct, we would have to introduce a divided by, not 24, divided by 4 factorial, 3 factorial, 2 factorial. These guys were already okay. The first two derivatives were totally good to go, but can we continue the pattern? I think we can. This could be 1 factorial. That won't change because that's 1. And this one is 0 factorial. And remember when we learned factorials last unit, we defined 0 factorial as 1. So does that actually make our graph better? Well, I don't know. We should probably go back to the graph and add those factorials, shouldn't we? So jumping back over here, I'm going to go ahead and divide by 0 factorial, divide by 1 factorial. Nothing's changed at all so far, but now is where our changes start. Divided by 2 factorial, I don't see much of a change there. 3 factorial, kind of shifted a little bit. 4 factorial, oh, look at that. Remember, this one caused us to be off by a rate of change of 24. And off by 24 with that many rate of changes has a pretty big effect. Putting that 4 factorial in, look how good my approximation is. It's maybe not great over here, but couldn't we just follow this pattern and add a couple more terms? Right? X to the 5th divided by 5 factorial. Oh, buddy, I can't even see the difference of the graph for a while now. And we could continue out. Now this has 1, 2, 3, 4, 5, has 6 terms. Well, what I've actually done is I've built this tangent function down below, and I'm going to go ahead and turn it on right now and show you what happens as we change out those terms. So I'm going to get rid of this guy, turn this one on. Currently, this is our same tangent function, but only with the first term in. Think of this 0 as the factorial for now, right? That only goes out to 0 factorial, or the 0th derivative. As I add more derivatives, look what happens. First derivative, tangent line. Second derivative, parabola, tangent parabola, polynomial approximation. Third, fourth, fifth, 6 terms. This is what we left off with before. But I went out to 50. Let's see what happens if I continue out there. Look at that function. Oh my gosh, isn't that getting really, really close to our actual function, right? This polynomial, and remember, my polynomial here does not use e at all, is getting more and more like e the more predictable terms that we put at the end. And I think you'll actually have a really tough time deciding which one is which over here. And so that's really, really powerful. And we're going to talk about that right now. Now, if we continue past that 4th derivative, right, and we could have continued past here, our polynomial approximation is 0 every time up here, right? If I continued past the 4th derivative, because there's nothing, everything becomes 0 after that, which we don't want because this is 1 all the way down. So what does that suggest about the number of terms we're going to need in our polynomial approximation to match all the derivatives over here forever? Well, hopefully you're looking at that going, oh, doesn't that mean we need an infinite polynomial approximation? And you're right. So we need an infinite number of terms. And actually, in this case, if you are able to write out this polynomial approximation with an infinite number of terms, then we can actually say that e to the x is exactly equal to our tangent. It's even wrong to call it an approximation, but I'm still going to use approximation, to our polynomial approximation. So just by putting this dot, dot, dot to show that we go forever, this is another way to represent e to the x. It is exactly equal. Now, one last connection here. Aren't we taking a pattern and then adding up an infinite number of terms in this pattern? Haven't we seen that before? Didn't we just spend like 2 months on it? Oh yeah, this idea of an infinite summation is known as an infinite series. Hey look, it's like everything's coming together. This is so cool. Now, what we're going to do on the next page is take these results and try to generalize how we could do this process for any function, not just e to the x. So here we go. Our most accurate polynomial approximation of any function, not just e to the x, of any function with some center, we centered ours at x equals 0 up above, is given by this. And this is exactly what we just did, right? We had f of a, so f of 0, times x minus 0 to the 0th over 0 factorial. But look at what they all have in common. In particular, 0 factorial, 0, and technically the 0th derivative. And that pattern continues. 1 factorial, first derivative 1, 2 factorial, second derivative 2, nth factorial, which would really, we'd take that to go to infinity to get our most accurate polynomial approximation, and we end up there. What else do they have in common? Well, notice that we are evaluating each function's derivative at a, and it's also x minus a. Think HK form, right? X minus h, x minus a, it's the center, and that's common every time too. So we have these two commonalities where these guys have to match, and then we have the trifecta that also has to match. And as we go through those, you'll get used to it. Now, one last thing to say here. I said the most accurate polynomial approximation, and on the previous page I said this is exactly e to the x. That is not always the case. There are many functions where we can get a very accurate polynomial approximation, but it will never perfectly match. And we'll go more into why that is later on. For now though, let's give this type of polynomial approximation a name. This polynomial approximation method is called Taylor Polynomials. It is essentially our fourth branch of calculus, where we have limits, derivatives, integrals, and although this whole branch is called power series, we really in BC just focus on Taylor polynomials. They are named after a famous mathematician, Brooke Taylor. He's from the early 18th century, so early 1700s. And it's important to remember in the early 1700s, they didn't have those fancy calculator things we have now. In fact, calculators have really only been around for 50 or so years. So you have to realize that in the early 1700s, they definitely had natural log, e to a power, sine, cosine, and they wanted a way to find values of those. But without a calculator, how do you find values of like sine of 6.5, e to a power of 3, natural log of 12? Well, it turns out that if you can rewrite e to the x without e and still get the same answer, then now we have a way to very accurately calculate a whole bunch of different values that previously we were only estimating. So, a Taylor polynomial centered around x equals a is often denoted as p sub n, where p stands for polynomial, and n is the number of derivatives we go out, and is given by p sub n of x is this guy over here. Now, full disclosure, I actually prefer to write it like this up here. They simplified, and they said 0 factorial and x minus a to the 0th. Why bother writing that? Well, I bother to write it because I like seeing the pattern every single time. This pattern repeats, and if we do the same pattern every time, we're more likely to remember the whole thing. However, if you like having to write a little bit less, you can totally start there and start to see the pattern eventually. You should notice that this p sub n of x is kind of tricky notation because of that n. It's very similar to s sub n, where n was our partial sum number, and in the partial sums, this n just matched the top of our series number, right? We were evaluating from something to like n equals 5, and so this meant go out until you get to an n of 5. S sub 5 didn't mean write 5 terms, it meant go out till you hit an n of 5. And if we had started at like an n of 2, then we'd only have 4 terms there, or 3 terms, or whatever. In a Taylor polynomial, p sub n means go out to that degree polynomial. It doesn't mean that number of terms. For example, p sub 0 of x would just mean we do the 0th derivative at a. I should use my space a little bit better. We do the 0th derivative of a over 0 factorial times x minus a to the 0th. This 0th power is a 0 degree polynomial. I would stop right there. If they asked for p sub 4 of x, well, we have to go a little bit further then. And again, the more you write this pattern, the better you're going to be at it, and you definitely need to memorize this pattern. It comes up all the time. So there is one term. My second term uses the first derivative, and it goes out to the first power. So that's a first degree polynomial. That would be like p sub 1 of x. Second derivative. This is now out to p sub 2 of x. Third derivative, p sub 3 of x, and fourth derivative. And you can use Roman numerals here. A lot of times they just use a 4 like this, so they don't have to write any more Roman numerals, but totally up to you. And so if they ask you for p sub 4 of x, look at the number of terms we have. 1, 2, 3, 4, 5 terms here. So don't let you think that this 4 is the number of terms. They want that 4 to be the largest exponent. And oftentimes what will happen here too, and you'll see this over the next couple of days, is some of these will become 0, and these will like cancel out, and you'll just be left with 3 terms. That's fine. This number doesn't matter about the number of terms. As long as you get up to a 4th power, you're good to go. All right, now a couple of concluding notes before we get some practice in here. I mentioned that polynomial approximations were originally designed to help with tricky functions like sine, cosine, exponentials, logs, all that fun stuff. Now, we're going to be discussing this more down the road. However, obviously, we will not be able to write out an infinite number of terms in our infinite series. However, the more terms we write, and we saw this on the previous graph, the more accurate our approximation is going to be. So keep that in mind, and we'll see this in just a bit. Now, although not required, and I did tell you that you'll need to memorize this guy up here, memorize that pattern. There are actually 4 Taylor, and I should write that, there are 4 Taylor polynomials that you'll need to memorize for AP Calculus BC besides the general form of a Taylor polynomial. So this is the general form up here. There are 4 specific Taylor polynomials you need to memorize. And based on the theme today, it should not shock you that the first Taylor polynomial you should memorize is the Taylor polynomial for the function e to the x centered at x equals 0. Now, I'm actually going to have you also write the Taylor polynomial centered at x equals 1 so we can compare the two and talk about which one we'd like to work with. But notice that they actually ask you to write 4 Taylor polynomials down here and 4 more over here, which could be a little obnoxious. So let's just start with the most complicated one, because as you'll see, working backwards is going to be really easy. So p sub 3 of x, this is our Taylor polynomial of e to the x centered at x equals 0. So what does this look like? Well, it's going to be f of 0, because we're centered at 0, divided by 0 factorial times x minus 0 to the 0th. Okay? F prime of 0 over 1 factorial x minus 0 to the 1st. We need a second derivative at 0, and we definitely need a third derivative at 0, and I think we get to stop after that, because now we're to a 3rd power, a 3rd degree. We already did this earlier, f of 0, f prime of 0. This is just e to the 0 over and over and over again. So we should know that, of course, this is 1. 0 factorial is 1. And then x to the 0th, right? 1 again over 1 factorial, x to the 1st. 1 over 2 factorial, which is just 2. And 1 over 3 factorial, 3 times 2 is 6, like so. And then cleaning this up a little bit further, this becomes 1. We know this is x. This is x squared over 2. I actually kind of prefer to write this as 2 factorial. I like leaving the factorials in there. It's a little less math you have to do. But you can, of course, keep it as 6 and 2 as well. Totally up to you. So there is my 3rd degree Taylor polynomial for e to the x centered at 0. Could we work backwards? Of course we could. This is the exact same polynomial as down below, but it only goes out to the 2nd power. So it's just the first 3 terms, right? 1 plus x squared over 2 factorial. And continuing back, 1 plus x, and just 1. This is just a line, a horizontal line, or diagonal line, parabola, cubic function. The more curvature, the more derivatives we add in there, the closer it's going to be to matching e to the x. Now let's look at the other guy. The other one's a little more complicated, and it might help to remind you of all the derivatives here, right? F of x is e to the x. In fact, all of these are e to the x, aren't they? I do usually start out like this if it's a little bit more of a complicated derivative. I like to find all the derivatives first, and then I like to evaluate all the derivatives at their x value. In particular, we are going to be centering t sub 3 of x at 1. So this becomes e to the first, which is just e. And in fact, hopefully you can see that all of these are e, but I'll put them out here just in case. That should be 1. I'm getting ahead of myself. Like so. Cool. Taylor Polynomial. General form first. Yes, I am going to write it again, and I suggest that you write this as many times as you need until you can memorize it, because oh my gosh, is it important. Well, here we go. So it becomes f of 1 over 0 factorial times x minus 1 to the 0th. And look at this. We have the double match here, and then we have the trifecta over here. 3 things match, 2 things match. And it's kind of tough to see when it's at 0, because you're like, don't 5 things match? Well, it's a little bit easier to see over here, right? You can see the double match that's here, and you can see that trifecta that's matching over here, 2 and 3. All right, as we continue through, we have f prime of 1 over 1 factorial times x minus 1 to the first. And you're like, ooh, 5 things match. Exciting, but not really. Double prime of 1, 2 factorial, x minus 1 squared. And now you can go back to those matches again. Third derivative, 3 factorial, x minus 1 cubed. All right, simplifying, putting everything down, I think we can probably skip to our last simplified step. F of 1 is e. Everything else becomes 1. So we get e plus e times x minus 1 plus e over 2 factorial times x minus 1 squared, e over 3 factorial times x minus 1 cubed. Now, let's compare these two. We have this guy right here and this guy right here. Which one to you looks more simple? Well, hopefully you said the one centered at 0. Now, it turns out that there's a little bit of an art at determining where you want to center your Taylor polynomial, because you can center them anywhere. It doesn't matter. I mean, there's small restrictions, but it generally doesn't matter. However, it does matter if you're trying to do this without a calculator. Now, hold on to that idea, because we need to see what we use these Taylor polynomials first for, and then we can start talking about that, not a calculator. For now, we're going to go down and try to write out the pattern for e to the x centered at 0 and e to the x centered at 1. We are also going to include the general term at the end, and then I'm going to remind you of what you need to memorize. So, p sub n was centered at x equals 0. It has a pretty darn predictable pattern, and I'm going to write in those factorials again. 1 over 0 factorial, x over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, plus ... Well, what's happening every time here? I think this pattern happens every time, so we definitely need a fraction. These two match, the 3 and the 3, so let's call those n. And then the x is actually constant every single time, so there's an x here. And you might say, well, there's no x over here. Well, there actually is. Technically, this is x to the 0th, but it's just 1. And I think this is our general term. Remember general terms from last, almost said last season, but yeah, last topic as well. We had to write general terms that just describes the pattern. You need to memorize this. This is the Taylor polynomial for e to the x centered at x equals 0. And in fact, it is exactly e to the x if you write out an infinite number of terms. If you don't write out an infinite number of terms, then it is approximately equal to e to the x. And in fact, we do need to use an approximately sign if we're saying e to the x is this guy, because we're never going to write out an infinite number of terms. T sub n, this one's a little trickier, but it's nothing too bad. I'll do this one in red, and I'll do it in black. Why not? So we have e over 0 factorial plus e to the x minus 1 over 1 factorial. And then hopefully we can start to see the pattern. E x minus 1 squared over 2 factorial, e x minus 1 cubed over 3 factorial. Let's get that general term. Think about what's constant. I think there's an e every time and there's an x minus 1 every time. What's changing? Well, the exponent and the factorial. And so we have our general term. Okay, I'll box this one in red so you can see the difference. You do not need to memorize the one in red. However, the one in red is also approximately e to the x. Both of these Taylor polynomials can be used to find values for e to the x. But which one would you want to use? Well, hopefully you're thinking the top one, because the top one doesn't have e. We can do all of the calculations of the one in yellow without a calculator. It might take us a while to do some cubes and squares, but we can get there. The one in red, you arguably have to use a calculator for, because every calculation involves e, which is an infinitely long irrational number, right? 2.71828 blah 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 blah. So if you had to choose between these two Taylor polynomials to evaluate e to the x, we definitely use the yellow one. In fact, almost nobody would ever use the red one, but I'm using it today just to show you the comparison. Now, I mentioned using these, so we should probably figure it out. Let's say that we wanted to evaluate, and this is kind of weird, it's the bottom. Let's say that we wanted to figure out the answer of e to the 0th. Now, this is kind of a silly question, because don't we know that e to the 0th is 1? Sure. Okay, well, what if I wanted to figure out e to the 0.5 without a calculator? That's the square root of e. Anyone know the square root of e off the top of their heads? I think probably you don't. But the nice part is, since we have a polynomial approximation that is the same as e, but doesn't use e, now we have a way to evaluate this without using a calculator. Of course, I'm promptly going to break that and use a calculator because I don't have enough time to work all these out by hand, but it does give you the idea that you can do this without a calculator. Now, let's go ahead and take a peek at this. I have set up two different polynomials on Desmos to help us out. In particular, I already showed you one of them. I showed you the Taylor polynomial approximation centered at x equals 0. And so if it's centered at 0, of course, these two share this point, right? Now, currently, this is out to, and I'm going to get rid of, let's actually move this a little bit. Let's move these guys down below so we can have a right next to it. There we go. Okay, currently, my blue line centered at 0, 0, 1 if you want, is only out to the 0th degree. That's just a horizontal line. It's only one term. Here is a second term, maybe. There we go. Third term, fourth term, fifth term, right? Fourth degree if you want, and so on and so forth. Okay, it gets more accurate the further we go. But you should also notice one thing as we go out. Doesn't it always contain the point 0, 1, right? Any Taylor polynomial, wherever you center it, is going to always contain that point. If I substitute 0 into my Taylor polynomial right here, or actually it's probably easier to see in this one up here, if I substitute in 0, it's going to cancel out every term except the first one. So we'll come back to that in a second. Now, what are we doing with this? Well, we're going to go ahead and fill this in. So we're going to say we want to find e to the 0th. Well, technically, to find e to the 0th, we'd go back to a polynomial to a degree of 0, which we actually did up here. And we'd say, okay, to find e to the 0th, if I wanted to use a less accurate polynomial, then I would just go to my polynomial approximation, replace x with 0, and there's just an answer here. That's just 1. Cool. If I wanted to find e to the 0th here, this is a first degree polynomial, and we get 1 plus 0, which is 1. Right? I think we're just going to get 1 every time here, actually. But showing you visually, what I'm doing here is f of 0, I've defined to be this guy. We should just put it right next to it. There we go. Apparently it dropped in there. That's not what I wanted to do. Please come back out. Thank you much. Okay. So f of 0 is basically saying, here's my polynomial function. I should probably call this f of x equals the Taylor polynomial approximation. So as I go out further, we sometimes will see this value change. But we just saw that f of 0, my Taylor polynomial, is going to be 1 every time, no matter how many terms we give. So this guy right here is going to be 1 every time. However, let's look at the Taylor polynomial not centered at 0. This Taylor polynomial is centered at 1. So let's give you a visual first. Turning off this one, and we're going to look at this one. You're going to get out of the way too. Cool. So, jumping up here, here is my new Taylor polynomial, maybe zooming out a bit, and it's centered at the point 1, x equals 1. So, currently, if I wanted to evaluate e to the 0th using the Taylor polynomial at 1, jumping back to this page over here, right? I apparently did not go back and write all these in, so that was silly. Let's do that right now. This is e plus e to the x minus 1, and this is e plus e to the x minus 1 plus e to the x minus 1 squared divided by 2 factorial. Whoops-a-daisies. Here we go. I wanted to figure out what is e to the 0th, and I wanted to use my Taylor polynomial centered at 1. Well, then I'd evaluate this Taylor polynomial at 0, right? And so this would just be e. So notice on my graph, right now, my Taylor polynomial at a 0th degree is telling me that e to the 0th is 2.718. And I think that's probably not right, is it? 2.718, so on and so forth. I'm getting e, actually. E to the 0th is 1. My Taylor polynomial gave me the wrong answer. Well, that's rude of it. What happens if I go further? What happens if I use my next one? Right? If I wanted to find e to the 0th and use a Taylor polynomial with more terms, well, then this would become e plus e to the 0 minus 1. That's e plus negative 1e. E minus e, that's 0. And double checking that, looking at Desmos, if I go out one more term here, I said one more term. Well, it is going out, and it's just not changing, apparently. There we go. Going out one more term, now notice that g of 0 is 0. Okay, well, that's what I got as well. What happens if I go out 2 terms? 1.359, I should probably record these down below. I have Desmos to do it for us. So we got 0. If we use the next one, we get 1.359. If I use the third and the fourth, here is the third degree, 0.906. And if I use the fourth degree, 1.019. So notice, using my Taylor polynomial centered at 1, originally the answers weren't very close to the actual value. But by the end of just going out 5 terms, I'm pretty darn close. 1.01, I'm off by approximately 1 or 2 100ths. Not bad at all. In fact, watch how g of 0 changes as I bring a out even further. Right? It's kind of oscillating, bouncing back and forth until I get to about 14 terms. Once I hit 14, it's still not perfect, but it's perfect for so many decimal places that Desmos just gives up and says, yeah, okay, it's 1, you win. So I still had to go out 14 terms, but that's not too bad. So what we might notice then is if they're asking for a value where your polynomial is not centered, right? They're asking us for what happens at 0, and we centered at 1. It takes a while for that orange function to get really close. Like right here, these two values are pretty darn close. Right? Here's that 0.906 and here's this one right here. But as we go further, the orange function gets closer and closer to the graph, and so our values get closer and closer together. Now again, this is a sort of a silly operation because we need to use a calculator here. But let's go ahead and do e to the 0.5. Neither function is centered at e to the 0.5. Let's actually look at the actual value of e to the 0.5. Rounded 1.648. Remember that, 1.648. Exciting. Let's compare each of their values for the different degree polynomials. And I should be able to see both of these at the same time. We are going to look for what happens at 0.5. And we're going to start with 0. Well, at 0, we get 1 and we get 2.718. 1 and 2.718. And if you actually use your functions, it won't shock you that you get both of those. At 1, we get 1.5 and 1.359. if we go to two terms, 1.625, 1.698, okay, going out to our third one, I should go up a little bit. Third degree, 1.645, 1.642. And the fourth degree, 1.648, 1.649. Look at that. It took me a power of 5, so 5 terms, I'm sorry, power of 4, so 5 terms to get my approximated value. And for none of these 5 terms did I ever have to use e. This was all polynomials. This was centered at 0, so it didn't start very close, but got closer and closer. This one was centered at 1. It also didn't start very close, but as we used more terms, it got closer and closer. Again, this one is a little harder because you have to use a calculator to get those values, but it really is illustrating the idea of a Taylor polynomial. Let's do this last one. This last one asks us for the value of e to the first. We know the value of e. It's 2.718, so on and so forth. And in fact, we can do a lot of this really quickly because they're asking us to evaluate e to the first. So e to the first plugged into a function centered at 1. Well, anytime you take a value and the function is centered at that value, then you're just going to get the first term, right? It's just going to be e all the way down. However, this guy's going to be a little different, so let's go ahead and see what happens if I plug 1 into my equation. So we're going to find f of 1, g of 1 is of course e, no shocker, and we're going to start at 0. F of 1 is 1, of course it's always that first term, then we get 2, and f of 1 is 2, and then we try 3, 2.5. Okay, third degree, 2.666, and the fourth one is 2.708. So this one actually took a little bit longer to get to e. It's not even accurate out to even 3 decimal places at this point. It's pretty close, but still not accurate. And that is an issue with some Taylor polynomials. In fact, some people think that calculators use Taylor polynomials to calculate values of e to the 0.5 and whatever. But because it takes so, in quotes, long for a Taylor polynomial to do a nice approximation of these values. Calculators these days just have, of course, a table where they look up all the values in their little mini hard drives. However, in other situations, they wouldn't use a Taylor polynomial because Taylor polynomials take too long to get here. There are other types of polynomial approximations or other approximations in general that calculators will use to figure out this, that get there faster, right? If I wanted to continue out here, 2.716, that's pretty good. That's pretty good. Well, look how many decimal places we have to go out to. Ending in 846. Still not at 846. Still not at... There we go. 846. I had to go out 14 to a degree of 14, so 15 terms to get there. And if I have to go out 15 terms to make it accurate to 10 decimal places, wouldn't you rather use an approximation where you only had to go out, say, 4 or 5 terms to get there? So are there better approximations than Taylor polynomials? Certainly. However, do Taylor polynomials work for every type of problem? Generally, yes, which is why we use them. So let's get our conclusion in. I have a quick corollary first. If a Taylor polynomial for a function is centered at x equals a, then if I plug that a value into my Taylor polynomial, in this case it was centered at 1, wasn't it? Or in this case up here, it was centered at 0. Then the value of my Taylor polynomial will be equal to the value of the function, right? When I plugged in where this was centered, it was automatically equal to the value of the function. Same thing over here, where it was centered was automatically equal to the value of the function. Okay. Another way you can think about it is really it's just because of like a tangent line, right? If we're centering it at this point, or if it's tangent at that point over here, right? And let's just say there's a tangent line right here. And then I ask you, what is the value of my tangent line at that point? Well, of course they're going to be the same. That is the point that they share with each other. All right, we're going to finish with a couple practice problems, then you guys will have a few to do on your own. So, number one, today we learned one of 4 Taylor polynomials you should memorize. In fact, we learned the approximation for e to the x, and in fact it is exactly equal here if you can write out an infinite number of terms. So we say e to the x is equal to, and then here's our pattern, 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus, forever out, x to the n divided by n factorial. Now technically, because this is ending, I should probably put approximately unless there was a limit saying n went to infinity. But either way, if you are able to write an infinite number of terms here, it is exactly equal to e to the x, except without using e, which is very cool. Number 2, does the accuracy of an approximation given by a Taylor polynomial generally increase or decrease with the number of terms? Well, we saw that on the graph. It definitely increases the more terms you have on there, and the main reason it increases is because it makes this approximation match this for all the derivatives, right? If we just have 4 terms to the 3rd power, then this will only match e to the x at its center down to 4 derivatives. We want it to match for all of the derivatives, so we want to put all of the terms. And you can phrase that however you'd like. Typically, how many terms does p sub 5 have? Well, p sub 5 means go out to the 5th derivative. And so if we start at the 1st derivative, right, something like this, I'm sorry, 0th, and then that's the 0th derivative, and then we put the 1st derivative first and go out to the end, well then this 5th derivative out here over 5 factorial times x minus a to the 5th power is actually the 6th term, right? We have 1 through 5, which is 5 terms, plus the 0th, which is the 6th. So normally something like this would be 6 terms. If any of the terms are 0, then there will of course be fewer than 6 terms, but the maximum we're going to have are 6 terms. The same way that p sub 7 will normally have 8 terms. Graphically explain what it means when a Taylor polynomial is centered on a point. Well, let's just look at the graph of e to the x, which looks something like this, and let's center a Taylor polynomial right here. We'll say a, comma, f of a. Well, if it's centered there, then it means no matter how much this graph matches or doesn't match at that point, those two share the same point, right? They share the same point the same way a tangent line shares the same point as the graph. And our whole goal with the Taylor polynomial is to make sure that all the properties of this point that are on the original function that I did in black are the same as on my Taylor polynomial, which I'll call t sub n of x over here. Last two, some practice ones. Find p sub 3 of x centered at x equals 0 for f of x equals the natural log of 1 minus x. And sorry for the bells, I'm recording at school today. Okay, well, p sub 3 means I need to go out to the 3rd derivative. So this is how I generally start mine. I start, and you're going to want to write a little small here. I start by finding each derivative and evaluating each derivative at the center. So let's start with f of x. F of x equals natural log of 1 minus x. And then I will need to evaluate that at the center. Natural log of 1 minus 0. Try to do this without a calculator. Any log of 1 is 0. Next one. I'll just alternate in colors so you can keep them straight. F prime of x is going to be the derivative. Derivative of natural log 1 divided by what's inside times the derivative of what's inside, which I think is negative 1. Now actually I'm going to write this, having done this problem a few times, I'm going to write this twice. Once as negative 1 divided by 1 minus x, and a second time bringing that 1 minus x up and saying it's to the negative 1st power. And I think you'll see why I do this in just a second. Okay, then we need to find f prime of 0. I think this one will be the easiest to use for f prime of 0. Negative 1 over 1 minus 0 is negative 1 over 1, which is negative 1. Cool. We're going to need the 2nd derivative. We can use all the colors, why not? Second derivative, well, to take the derivative, you could do the derivative of this, or this, or this. But hopefully you realize that our last function is the easiest to take the derivative of. So to take the derivative of this last function here, the negative 1 will come down. This will make it a positive 1 minus x to the negative second, times the derivative of the inside, which is an extra negative 1. So again, this, I'll move the negative 1 to the front. It becomes negative 1 minus x to the negative second, or negative 1 over 1 minus x squared. All right, now f double prime of 0, I'll probably use this last guy over here. So it becomes negative 1 over 1 minus 0 squared, negative 1 over 1, which is negative 1. And you're like, whoa, will the derivative of this be negative 1 every time? Well, no, it won't. We need one more derivative here. So third derivative, I'll do the derivative, not of that one, I'll do it of this one. I think the negative 2 comes down, makes it a positive 2, 1 minus x to the negative 3, times the derivative of the inside. So I think this becomes negative 2 times 1 minus x to the negative third, or negative 2 divided by 1 minus x cubed. F triple prime of 0, negative 1 over 1 minus 0 cubed. Not negative 1, I wish I could write, negative 2 over 1, which is negative 2. Haha, we've changed now. And in fact, maybe you'll see that the next one is going to be negative 6, and then after that, negative 24, negative 120. All right, I think actually what's happening is we're getting some factorials here. Sorry, my phone rang and we're still continuing on through here. So yeah, we're getting some factorials here. So as we go through and finish this off, let's go ahead and look at our centered approximation at 0. So essentially what we're saying is the natural log of 1 minus x can be approximated by using the following function. So we have, and I'll try to keep my colors consistent here, it's going to be f of 0 divided by 0 factorial times x minus 0 to the 0th. Plus f prime of 0 divided by 1 factorial times x minus 0 to the first, plus f double prime, tough to find the red, 2 factorial x minus 0 squared, and last but not least, plus f triple prime of 0 divided by 3 factorial times x minus 0 cubed. Or, putting this all in, the natural log of 1 minus x is going to be approximated. We do need that approximately. They are not equal to each other. The AP exam is very picky about those equal signs. And again, keeping those colors. We saw that f of 0 is just 0. So in fact, I think this entire thing is just going to turn to 0 because that's 0. Right? Plus f prime of 0 is negative 1. Negative 1 over 1 is negative 1. So actually I'll change this to a minus 1 x to the first, so just x. Plus, oh wait, the next one's going to be negative 2, isn't it? So minus 1/2 x squared. And then the last one, people getting paged, very exciting. And then the last one is f triple prime, also negative, so minus 2, this is 2, we saw that up here, 3 times 2 is 6, 2, 6, that's going to be 1/3 x cubed. And by simplifying here, I think actually you should be able to see this pattern. It looks pretty easy, doesn't it? Minus 1/3 x cubed, minus 1/4 x to the 4th, minus 1/5 x to the 5th. I bet the general term would not be too hard here either. But this is our P sub 3, our third degree Taylor polynomial approximation for the natural log of 1 minus x. Last but not least, one more practice one. Find the third degree polynomial centered at x equals 0 for f of x equals x cubed. All right, same thing, though I think we can go pretty quickly here. We'll do this all in one line. F of x equals x cubed. I'm going to find the couple derivatives here. F prime is 3x squared. F double prime is 6x. And f triple prime is 6. Cool. And then we need to evaluate each of these at 0. So f of 0, well, that's 0. F prime of 0, that's also 0. This is turning out to be a fun function. 0, f triple prime, hallelujah, we didn't get 0, we got 6. Okay, so we're going to say that x cubed can be approximated. Same pattern again. Keep writing it. The more you write it, the more you're going to remember it, right? First derivative, okay, second derivative, and third derivative. Simplifying this down, x cubed is approximately equal to, well, that's 0. That's 0. That's 0. Woof, this one's an easy one. 6 over 3 factorial x minus 0 cubed. So x cubed is approximately equal to, can we clean this up? Let's see, 3 factorial is 6. 6 over 6 is 1. X cubed, oh, isn't that just x cubed? Did we just go in a big circle? Well, not really, because x cubed is already a polynomial. And if we're going to write a polynomial approximation for a polynomial, then eventually, if we go out far enough, our polynomial approximation will always match a polynomial because we're just rewriting it. The far enough was we needed to go out to a third degree approximation to match this third degree. Notice anything further than that, right? The fourth derivative up here would be 0 because the derivative of 6 is 0. Any derivative after would be 0 as well. So the cool part about polynomial approximations is that for polynomials, they will always match. So it's actually appropriate to say x cubed equals this exactly, which is also why we generally don't write polynomial approximations for polynomials. That's just silly, because a polynomial approximation for a polynomial is just going to be the same thing. The point of a polynomial approximation is to approximate functions that are not polynomials, sine, cosine, natural log, all that fun stuff. So to finish off today, you guys just have a little matching assignment down at the bottom, 1 through 6. However, I do actually want you to find those second degree Taylor polynomials centered at 0 for each of these. So you're going to have to take 2 derivatives, first derivative, second derivative of each one. It's good derivative practice, and I will tell you that if they are not matching up, it's probably because you made a mistake on one of your derivatives somewhere. If I did make a mistake, or if you just can't figure one out, please email me, let me know, and we'll go from there. Next class, we're going to learn 2 more Taylor polynomials that you'll need to memorize out of your 4 total. So make sure to tune in, and I'm excited to continue through this adventure of power series. Actually, what is a power series? We'll learn that sometime soon. Promise.